So we've been seeing recursive functions. We started to see the power of them. They're really a powerful way of thinking about breaking a problem down into simpler pieces. And as we saw with things like Towers of Hanoi, what looks like a very complex problem sometimes has a beautiful solution by thinking recursively in terms of smaller versions of the same problem. We're going to do one more example, because so far what we've really focused on is things dealing with numbers. And while that's great, we can use recursion in other places. So here's an example of doing recursion on non-numerical values. In particular, suppose we're given a string of characters, and we'd like to know, is it a palindrome? And if you don't remember, a palindrome says, does it read the same left to right and right to left? Is it the same in either order? Classic example, attributed supposedly to Napoleon, although that's highly unlikely, is something like, able was I ere I saw Elba. And if you look at it on the slide, you'll see if I read it from left to right or from right to left, it's exactly the same. Another wonderful example, are we not drawn onward, we few, drawn onward to new era? Another great example of a palindrome. So, we're going to try and build this. We're going to do it, though, in a couple of stages. First one is we're going to strip out all of the spaces, the punctuation, because they don't really matter. We just want to know, are the characters the same? And secondly, we don't care about capitalization, so we're going to reduce all of the characters to lowercase. And then we're going to tackle this problem in terms of a recursive function. So, how do we solve it? We first convert the string to just characters. We'll look at that in a second. And solving it recursively is actually pretty easy. If I have a string that's either of length 0 or of length 1, it's a palindrome. So length 1 is just one character. Otherwise, to solve this, what I'm going to do is take the string and ask the following question. If the first and last character are the same, then they satisfy the condition. And let me then simply look at the remaining string, throwing away the first and last character, and ask, is that a palindrome? Wonderful. There's that recursive property again. If I can break it down into that problem, I'm set. So, I could write code to do that. Just to give you the example again, this says I'm going to take something like able was I ere I saw Elba and reduce it to just that string of characters without the spaces or any punctuation. And then to test whether that string is a palindrome, that's the same as asking, are the first and last characters the same? Is that test? And if I take everything else in between, I can ask, is that also a palindrome? If the answer to both of those is true, then the bigger problem is also palindrome, and I'm done. Okay, so here's the code to deal with it. And there's a few new things I want to point out here. I'm defining is palindrome to be procedure. Inside of there, I've got two definitions for other procedures. And that's a little different. These are now called internal procedures. But this is perfectly fine. These are quite straightforward ways of creating new procedures. And in particular, they are going to belong only to this function. If you think about our environment model, when I call is palindrome, it's going to evaluate the body, which is going to cause these two definitions to be evaluated and created, and the bindings for those names is going to be within the frame resulting from the call to is palindrome. So only is palindrome has access to those. This is a nice way to capture functions if they're really only going to belong to a single function. The first one is just doing what I asked earlier, that is to convert this string into just a set of characters. A couple of things I want to point out here. The first one is right here. Here we're actually using a method of a string. We're going to come back to that later in the term. But it simply says, given that S is a string, the dot notation says get the method called lower associated with that. That is a procedure or a method, so I'm going to call it by giving an open and closed paren after it. And in essence what that does is it uses a particular internal procedure or method or function to convert S into all lowercase. And I'm going to rebind that to S over here. Then I'm just going to run through a loop. I'm going to store in ANS or answer a string of all of the characters. And for each character in that converted S, I run through a loop where I first check to see is it one of the lowercase characters. So C in that string literally basically says for each character in there I return, if it is in there I return an answer. If it's not in there I don't add it in. And this loop lets me walk through all the characters in S, keeping only those that are lowercase values, and I just return the answer. All right, some housekeeping. Palindrome, or is pal, the actual checking, is exactly what I would expect. It says if I've got something of length less than or equal to 1, it's a 0 or a 1, the answer is true, it is a palindrome. And otherwise, notice what I do. I use the properties of strings. I get the first and last character, and I say, are those the same? And if they are, I then also ask, is everything else the same? And notice this slicing right here. This pulls out the substring out of S, starting at the first, not zeroth element, and stopping just before the last one. So getting everything but the first and last character. And there's the recursive call. And then finally, isPalindrome simply uses two chars to convert the string, calls isPal on that, and returns the answer computed by that as the answer to the overall solution. And if we want to actually check this, we can. If I go over to my idle window and I load this in, I can now say is palindrome, and I will give it some simple examples. So let's do A, B, B, A. That should be a palindrome, and it is. I'm going to ask if my colleague John Guttag has a last name that is a palindrome, and the answer is close, but not quite. If he changes his name, which he will not do, to Guttag, it is a palindrome rather. And finally, just as one last example, let's look at Able was I ere I saw Elba, and that is also a palindrome. And this is doing exactly the kinds of things we would have expected. Now, this is a nice example of a broader kind of problem. This is, as some of the other things have been, is an example of what we call a divide and conquer algorithm. And that kind of approach says to solve a hard problem, we can do that by breaking it into a set of subproblems, more than one, with the property that the subproblems are easier to solve than the original one, either because they're a smaller version of the same problem, or they may just be an easier subproblem to solve, and that the solutions of the subproblems can be combined to solve the original. In the case of testing palindromes, I'm checking two things: an easier test on the first and last character, and a simpler version of the same problem. And the answer to both of those combines together to give me the answer to the overall problem. We're going to come back to these ideas of divide and conquer algorithms later on. They are an incredibly powerful tool that we're going to use in many places to solve interesting and challenging problems.